Hello and good morning.
Good morning.
How are you all doing today?
I'm doing fine. And you?
Good, good. Ready to get started. We'll start today actually with a quiz because I want to see how you guys are doing and if you're catching on to some of the important points. So what I'm going to do is in the chat, I'm going to go ahead and paste a link. And then when you click on that link, it should take you to a form. And there are like two questions that I've got in today's quiz, both of them about temperature anomalies. So go ahead and click on that if you could. And it's just a short 10-point quiz, not worth a lot of points. I just kind of want to see where you're at. We'll do a lot of these short little quizzes at the beginning of each class, and it almost always covers what we talked about in the last class. So it's helpful to, if for some reason you missed it, make sure that you watch the lecture that's posted online in Moodle. And for those that aren't in Moodle yet, I've been trying to send out links for those. So make sure to put your name in it. And then the first question is, what is a temperature anomaly? And describe it, what it is and how it's calculated. And then the second question, quiz question is, what are the advantages of using temperature anomalies to talk about climate change rather than absolute temperature? Mungo, I see you're just joining us. Folks are taking a quiz. If you go to the chat, I've pasted in a link. If you click on that link, that'll take you to a form. It's got two quiz questions on it about temperature anomalies. Hi, Desire. I see you're just joining us now. Folks are taking a quiz. So if you could go to the chat, I'm pasting in a link. If you click on that link, that'll take you to a form where you can answer the quiz questions. There's two of them on temperature anomalies.
Okay, thank you.
I've already got one response turned in. Okay, I'll give you about 1 more minute to finish the quiz and submit your responses. Brenda, I'm going to paste in a YouTube link to the last lecture. Please have a watch as soon as you can, certainly before the next class. Okay, if everybody could go ahead and submit what they've got, I'd appreciate it. So Caldrian and Brenda have turned in theirs. Desire and Imungo, if you could just go ahead and submit yours, we'll give it a little chat. One more. Please finish up. So I'm going to close out the quiz. Okay, closing out the quiz. Hit send or not at all. So temperature anomaly. Best way to describe it, it's if you're trying to determine a temperature anomaly, say for this month, for the month of August, in this year, what you would do is you have to pick a reference range sometime in the past. So a common reference range that's used is the 1951 to 1980 average. So it usually a multi-decadal long period is really good to choose for your reference period. So you want a long period of time. And one of the answers, it was mentioned that the anomaly is departure from a reference value calculated by some period in the past. It's got to be a multi-decadal period. Otherwise, it's not valid. So you take some reference time frame, get the averages for that. So if we're talking about the month of August, so from the period of 1951 to 1980, you'd average all the temperatures for the Augusts of those years. That will give you a reference number, and you'll subtract that from the average from this current month, and that will give you what we would call the anomaly. A positive anomaly, which would mean the average is higher, a negative anomaly, which would mean the average is cooler. And the main reason why we use these is because temperature, absolute temperature, can vary widely in just tens of meters. So if you look at a heat map of a city, we'll look at it again, you'll see that you can go about 20, 30 meters, and there's a very different absolute temperature. And that can be true over tens of meters or hundreds of meters. And in order to get a good assessment, if you're using absolute temperature, you'd need hundreds of thermometers, if not thousands of thermometers, placed tens of meters apart to get all these different temperatures. But with the temperature anomaly, since we're kind of looking for a trend, something that influences general temperature all over, you would expect if one area is measuring 1 degree warmer, then the areas close around it are also measuring 1 degree warmer, even though the absolute temperatures might be quite different. And this is often caused by a heat island effect. So the advantages of using temperature anomalies is that it adjusts out for local temperature variations, and it can look in a larger area. It also means you need fewer thermometers to measure temperature changes in a region. Whereas you might have needed millions of thermometers to do a city, you might need only one thermometer to do that city. Because of using anomalies. Does that make sense to everybody? This is a really key point because we use anomalies over and over, and it's really important to understand exactly how an anomaly is calculated and how it's referred to and what its advantages are. And so if you have any difficulty with that, please go back over the last lecture where we talk about anomalies in detail, or email me, or we can do a Zoom together, whatever. But I want to make sure you're all up to speed on exactly what those are. So I'm going to go ahead and start today's lecture. And so we're going to now talk about the single most important data set that we're going to be using throughout this course. It's the foundational data set for climate change. It's the surface thermometer record. And then later on, we'll get into other records that support our findings in global warming. And from all this work, by the end of this, you should be able to describe how the surface thermometer record is collected, how it's adjusted. That's really important. You need to be able to talk about why it's adjusted and how it's adjusted, and how. You'll also, at the end of these lectures, be able to talk about other independent data sets that confirm the same kind of conclusions that we get from the thermometer data, and how those data sets are measured and what their main conclusions are. Okay. So let's start with the surface thermometer record. Everybody knows what one of these are, and that's kind of the point. Is this is based on centuries old technologies, the liquid glass thermometer. Everybody knows how to use one. They've been in use for centuries. They're readily available all over the world. They're very accurate, and people have been measuring temperature and writing them down for centuries and centuries. And we've had probably sufficient coverage across the world since the 1850s. And remember, from what we talked about in calculating anomalies, anomalies allow you to use fewer thermometers to calculate the change in temperature trend in a region. And so it took till about the 1850s, about mid 19th century, before we had enough thermometers regularly being recorded to have sufficient coverage to be considered global coverage. And so this is how we're going to be calculating our global temperature anomalies. And I showed this picture last time. This is the global temperature anomaly. The reference period in this case is between 1951 and 1980. And so how they calculated this again is they looked at 1951 through 1980, and each thermometer station, they've got a record for that, and they calculate the averages between 1951 and 1980 for that thermometer at that station, and they come up with an average. Different stations will have different averages because of their absolute temperature. And now, when you now compare to present day temperature to calculate your anomaly, the difference between then and now, you then subtract that amount from the average temperature that you're getting at those same thermometers. Okay, so each thermometer is being subtracted by the previous measurements at that thermometer to calculate that anomaly. And what this is showing us is that since the mid 1900 or the mid 19th century, we've seen about a 1.1 degrees Celsius anomaly in the present day. Now that number is really important. I need you to remember that it's slightly higher than the value in the textbook. That's just because this is based on more current data. Also depends on which edition of the textbook you have. So 1.1 degrees Celsius is the warming we've seen since the 1850s. And that's a really important number to know because it's really our best measure of what the change has been like since the late 19th century. Any questions on this or how it's calculated? It would be really helpful for me when I'm giving these talks if you would turn on your cams. Sometimes I feel like I'm talking to an empty room. So please, if you can, keep on your cams. This way it kind of feels like there's a class here. Okay. Now, this is the global temperature anomaly with average temperatures, or again, averaging the different temperatures around the world. But if you look at it on a map, that anomaly, those anomalies aren't spread equally. Okay, so there are regions that that are warmer and regions that are cooler. The warming hasn't been uniform. And so here's a graph that's showing by different latitudes what those warming trends are, what those anomalies are. So here's our anomaly on this side. You can see for vast majority, you can have 1 or under 1, depending. You'll see that the southern hemisphere has not warmed nearly as much as the northern hemisphere. Any idea why that is?
Is it due to the Southern Hemisphere housing more countries? And what comes with that? I know the Americas and the more southern countries, there's a lot of industrialization. So could burning fossil fuels kind of be a?
Wouldn't
Is it
that
just
make it warmer then if it was
yeah?
industrialization? Wouldn't it make it warmer? We're seeing it's cooler in the southern hemisphere. So if you look at this red on
Oh,
here,
oh, I meant the northern. I meant the northern.
okay.
Excuse me. The
Um,
northern is a lot warmer
so
as
when you
opposed to
say more countries, I tell you, I mean there's more people. If you
yes.
look at it, indeed it has to do with land mass. So
Yeah.
we know that
Yeah.
land areas warm a lot more than oceans do. Okay, and most of the land mass on our planet is in the northern hemisphere by a large amount. And part of the reason why land areas warm more than ocean is made of water, and water has a high specific heat. In other words, it takes a lot of energy, a lot of heat to be put into an amount of water to raise it 1 degree Celsius, more so than other solids, than on land and such. And so you can put a lot of heat into the ocean and its temperature will rise slightly. That's not the same. That's true on land, where you have a lot more absorption of that energy. And so we see a lot more heating in the northern hemisphere. Warming is greater than in the southern hemisphere. In fact, the greatest warming that we see is up in the Arctic. You can see up here where it's darkest. Here we actually see a temperature anomaly between now and the late 19th century of close to 3 degrees Celsius. That's a lot more, a lot larger than the worldwide average of only 1.1. And so, you got to think about what that means and, what it might suggest for that area of the globe. And we'll get to that when we look at things like melting ice and other factors. So when discussing the surface thermometer record, one really needs to think a lot about issues in measuring temperature. Now, I had mentioned something before in urban heat island effects. We talked in the last lecture that temperatures can vary over great distances. Here's a satellite map of Atlanta, Georgia. We saw this last time. And then here's a satellite heat map of that same area. And you can see how where you have more of the city development, there's more concrete, there's more buildings. Those are going to absorb heat and get hotter a lot faster than, say, areas covered in vegetation. And so you can, again, have big, strong temperature differences over really, really short areas. If you look, at the little scale over here, this is a 5-kilometer scale. And so just within 5 kilometers, you can see, really surprising differences in temperature. So by using anomalies, we get past that, because if the overall temperature is rising by a degree, it should rise by a degree in the city center and out in where you've got these vegetation, okay? But one might expect, if it's true of heat islands, that if you're in the middle of a city where there's lots of concrete and buildings, that it's going to be warmer, then you might think that it could cause a trend in the overall temperature data, when we're going from the 1850s all the way to present day. Why would that be the case? Why would it create a trend?
A trend when I'm assuming you're asking when it's kind of totaling out for the entire or for this particular area of the city, or the discrepancy between the city temperature and I'm assuming the vegetative suburb temperature, or
So it could lead to a miscalculation in global warming. Because think about it. So here's a map of College Station, Texas. This is a satellite map from 1984. Now imagine we stick a thermometer right over here in this fairly rural part that's like a suburb of College Station. Now that's in 1984. Now over the course of time, the city develops, urbanizes, more people move to the city, population increases, they have to build more buildings, have to build more roads. And here's that same College Station only in 2016. And I'll go back and forth so you can see the difference. Here it's mostly vegetative, but over the course of these 22 years, you see that now it's become urbanized. So what would you expect to see in terms of a trend for that record in that thermometer?
It would definitely show average temperature increase due to really the urbanization over a 20-year period. So they could be kind of it could kind of show a skewed sense of temperature increase within this particular area. And that's simply due to the urbanization. Of course, it's going to become a lot hotter with the more industrialization in this area.
Right. So you'd see a warming trend in the data. Does that have anything to do with climate change?
Essentially, no,
No.
not overall, no.
No. And we want to be really careful, when we
Sure.
look at these temperature records to make sure that we're not building stuff into the cake and tilting in a particular direction. Certainly folks who are anti-climate change and have vested interests in discrediting the science are going to point to these things, and they often do. And so climate scientists have to adjust for this if you want to do this correctly. And so they do this, they adjust it, and this is how they go about doing it. So here's a raw data set. This is taken for Dallas, Texas, Love Field Airport. And this is their temperature record all the way back as far as 1900. You can see there's a period where they weren't taking any temperatures. And this is just one station, one thermometer over a period of time. So the first thing that they have to do is they have to pull out obviously wrong data, or what we would call outliers, right? So you can tell where the outlier in this one is, right? This obviously is an errant measurement, right? This one over here, way out of the norm on either sides. So they'll pull out, that could be, something happened with that thermometer at that point, whether it was placed or not. And then to adjust the data, we've already learned with temperature anomalies that if an area is warming due to actual global warming, that would be true in a region, not just at that single thermometer. So they have to compare this station to nearby stations. Okay. And so here's where they're comparing it to nearby stations and basically kind of averaging out and checking the data to see what kind of data they get, as compared to other nearby stations. Okay. They subtract the measurements from the nearby stations, and if there are anomalies, those should hold true over large distances, and we would expect to see no trend at all. Right? Okay. So let's break this down. Okay. So here is after the adjustments. Here's the in red is the temperature at that station, the 12-month average. The regional expectation is shown in blue. So this is, you can see that these are matching the regional expectations. Right? It means the other areas around it are of similar variations in temperature. And then in the gray line, this is the global land average. Okay. And so one of the things you'll find with these temperature adjustments is they usually adjust things to be less dramatic. They'll usually tend to reduce the trend that you see. So the unadjusted data was indicating a 1.8 degree per century rise, whereas the adjusted data is only about a 0.7 degree century rise at this station. Okay. And so adjustments generally tend to reduce the trend. Okay. And so climate scientists then have to do this adjustment for thousands of stations all around the world and average them. So every station, they do this kind of comparison. They look at the climate record for the thermometer at that station. They remove obvious blips or outliers. They compare the measurements at that station for the stations close by, because all of those should have a similar trend, if you will. And they can subtract that out to give them a true measure of what that anomaly is. And so they do this adjustment all over the world, average them, and then that gives us this graph that we were looking at before. And so a lot of effort really goes into producing that graph, one tending to pull out, the heat island effect, subtract for that heat island effect, because remember, when you're comparing it to stations around it, you're removing those, like the effect of urbanization, for example, of one particular thermometer going up. Well, let me stop that. To stop the fact that urbanization may be affecting one thermometer, it's not doing so to all the thermometers in the local region, because not everything has become urbanized. So all of that goes into when we look at these mean global temperatures. It requires lots of adjustments. Now, one can wonder about bias. People are adjusting the data. I've seen several articles claiming that global warming is a hoax, because scientists are adjusting the data to make it look poorly, to make it emphasize global warming. It's interesting because the adjustments tend to go in the opposite direction. The key here is that it's not just one scientific group. There's lots of independent scientists who use their own algorithms to adjust the data, to identify outliers, to compare it to the regional differences, so they can get what they think are accurate measurements of the record, the thermometer data for any particular station or any particular region. And so you've got some of these groups are many scientists, can be hundreds of scientists working on a data set. And then you get another group of 100 scientists working on the same data set, but they're doing it independently. And so what I'm showing you here, this is a comparison of different independent groups. NASA, NOAA, Berkeley, Copernicus, a variety of different groups, large teams working on the data, making those adjustments to then kind of filter out any problems in the data. Now, one of the things you'll notice is they all track really well. Okay, so these are done by independent researchers with their own algorithms. And if you take a look, like if you look towards past the 1950s, how amazingly well these things track. Okay, so remember what we said in our first lecture when we were talking about the IPCC and the scientific process and the crucible of science. When you have many independent researchers coming up with the same results, that tends to give you a lot of confidence in what that result is. And so, let's see. The other thing, besides the adjustments tend to agree, is that all those scientists publish the raw data and they publish their adjustment algorithms. And that's not all. If you go back to this, in the dotted line here, I actually have the raw data as well before any kind of adjustments. And you can see, except for between the period of 1900 and 1930s, you see a huge amount of agreement with the raw records. They're essentially giving you the same conclusion that you would even without the adjusted data. But again, if you don't adjust the data, people can say, well, what about heat island effects and urbanization? What about you know, thermometers that aren't properly being taken care of, etc. And so that's adjusted here. And so this gives us a pretty high confidence measurement of what the temperature anomaly is globally, because we have so many different groups coming up with the same data, adjusting it a variety of different ways to kind of come up with this. But so do you find this convincing, this data convincing?
I personally think it is convincing because having factored the anomalies that certain measuring, I mean the thermometer stations, it gives us a solid ground on debating people that will bring up like certain ideas that are contrary to what we go for, having taken all their approach,
Right.
leaving us with something solid, and it would make a sensible argument that would give us concrete evidence of what's happening.
Right. And the actual numbers, the quantities do matter, because eventually, and we'll get into this in later chapters, we're going to want to build models and try and understand, well, if you increase greenhouse gases by X amount, how much of a temperature rise should you see? A lot of those will depend on, what we've seen in the past. And so we'll need really accurate measurements of those. And by having many different groups trying to come up with those numbers, and if there's great correlation between those, then we can have a fair amount of confidence in the numbers that we're going to plug in to make calculations later on in the course. But that's not to say there aren't people that will say crazy stuff. So I'm going to play a little clip right now. This is of one of our politicians here in the U.S. This is Senator Cruz from Texas, I believe. Let me know if you can't hear this.
Partisan agenda.
Let's get back to climate change.
Well, I'm happy to. And my view on this and everything else is that we should follow the evidence and the science and the data. I'm the chairman of the Science and Space Committee of the Senate Commerce Committee. And I'm also the child of two mathematicians. Both my parents are mathematicians. My dad was a geophysicist for many, many years. And the problem with this debate is it is driven principally by people with partisan agendas in Washington that are disconnected from the science and the data.
What about the Pope?
And so let me talk about what the science and the data show. Satellite data show for the last 17 years, there has been no significant recorded warming. None. Now, that's a real problem, because the whole basis of global warming alarmism was based on computer models that showed there was going to be significant warming. And the problem is the satellites, when they're measuring the temperature, it's not happening.
Okay. So what do you think about that comment? Let's take a look at that setup. I mean, first you're like, oh my, right? But here, let's take a look at the actual satellite record that he's talking about. So here's the satellite temperature record. That's often used when people say, oh, global warming has stopped. There's been no warming. And so and that interview was recorded in 2015, and he said over the last 17 years. So he's talking about a specific period in time, right? From 1998, which is where you see this little blip right over here, to about 2015 to about here, okay? So he's talking about this region. And let's blow this up. So this is 1998 to 2015. And if you look at this, I don't think it's unreasonable to say that during this period, I don't see any particular trend. There's variation up and down, but there's not a lot, right? So what's going on? I mean, you all said that you believe in the warming, but now we see this. Has Cruz convinced you that this class is moot and we don't need to have this class?
Um, well, I could rebuttal with satellite temperature record. What specific is this the entire globe or is this a particular area? Um,
This is the calculated temperature anomaly based on the satellite record. We haven't talked a lot about the satellite record, but it's based on the satellite record, average temperatures around the world over this period of time.
well, just looking at the graph in of itself, with the highs and lows averaged out, there's not really much of a change.
There isn't. There isn't. And it would be hard to refute that. And that's how these folks get really
But
clever. And one of the things that I really want to teach you in this course is how to see through these kinds of things. Okay. So the first thing to take into account is that there's climate variability. There's always climate variability. There's different things that can affect the climate for a short period of time, short durational changes. You can have El Niños. We know that those tend to make, and here was a El Nino in 1998. That's where we get the spike. We get La Niñas, which tend to make things colder. So you can see the effects of the El Niños, La Niñas over here. Those things, again, they're over a short period of times. The effect of this El Nino was fairly short-lived, over a year period. That's about it. Same thing with the La Niñas, although you have several of them. Other things that can affect the climate are things like volcanoes. You'll get a volcanic eruption that will spew lots of dust into space. And later on in the next chapter, when we start talking about the physics of climate change, that that dust in space will increase what we call the albedo, where basically it will reflect more of the sunlight coming from the sun back out into space, so it doesn't come hit the ground, and so it doesn't warm us up. And so volcanic eruptions can lead to much cooler periods, can lead to cooling, but again, those only last a short period of time. And so here's where the logical fallacy comes, the problem with Senator Cruz's arguments come in, is if we're looking for a trend, okay, here we're showing a trend 1980 up. If we're looking for any kind of trend in a temperature record, that's what the graph would look like, right? It would be a line that's got a slope to it that's increasing. If we have climate variability, however, you'd see a lot of up, down, up, down, up, down, up, down, up, down. That's your short-term variability, right? So you could have a long-term trend, short-term variability. Those are the two things you're looking for. Now, if you have both, if you have a trend and you have short-term variations, you'll have a graph. You add those two together, it looks something like this, where there's a trend eventually going up, but then there's this variability going up and down and up and down and up and down. It's always possible to find the reverse trend based on where you pick your time points. So, for example, if I decided I'm going to look at a certain time period from, say, 1990 to 2003 or 2005, between here and here, look, the world is cooling, right? I can go over here and do the same thing. Let me move this little thing over here. Look, in this time period, the world is cooling. Oh, look, in this time period, the world, every time period I pick, the world is cooling. There is no such thing as global warming. What's the problem here? I'm picking all these periods and I see cooling in each one of the periods that I'm picking. So why can't I say as fact that the Earth has been cooling for the last, I don't know, 40 years, according to this graph?
Because the sample size is so small, and they're intentionally picking points where
Aha. Yes, exactly. I selected, so a lot of it has to do with how you pick your time periods, right? Often this is called going down the up escalator. So we know the trend is going up, but by judiciously picking your time points, by cherry picking your time points, you can pick a high point and then a low point to make your argument. And so one of the things that tee you off or clue you on to these kinds of fallacies is they pick short comparison periods, right? Remember when we were talking about anomalies, how long of a period did we pick as a reference period?
At least 30.
Yeah, 30 years, right? 3 decades long. Reason for that, because you want to mute out this variability that you get from things like La Nina and El Nino and volcanoes, etc. There's still, by selecting long periods, the true trend becomes clear. Now, if you have a long period, I can pick the high point over here and the low point over here, and I still see a trend, right?
Yeah.
And so that's one of the major things to think about by selecting these long time periods. You'll still see the same trend that you're looking for. Okay. But one of the things that's also interesting, besides picking that specific date, so we'll go back to that original satellite photo. Let's see. Let's see, where's the satellite photo? The satellite record here. By picking this date here and this date over here, which is where we were at, we saw really little. But if he had gone further back to the beginning of the satellite data, we'd be actually seeing a trend here, right? We can always pick a warm year and then select and compare it to a cold year. Okay. But beyond that, Cruz did something a little bit more disingenuous. Remember, he mentioned if you look at the satellite record, well, if you look at the surface thermometer record, that one does show a clear trend of warming. So we're talking about going from this region to this region. So not only did he cherry pick the data points and do the going down the upper escalator argument, he also selected one of the data sets, and cherry picked that for a region. Okay. Makes sense? Okay. Now, you should remember that our surface thermometer record is the main data set that we're going to use. It's probably the most reliable because it has the most measurements over the longest period of time. Okay. But still, scientists don't want to stop there. As we talked about when we were talking about how science works, in the first lecture, we like our conclusions to be verified multiple times, hopefully by a lot of different sources in a lot of different ways. So there should be other data sets that we can use to confirm this kind of warming. Now, we rely on the thermometer record in part because some of the other ones that we're going to talk about are actually effects of the thermometer, of the temperature. So, for example, some of the other data sets that we're going to look at the satellite record, we're going to look at the ice record, bulk ocean temperature record, and sea level record. Okay. It's 11:50 now, so we'll stop. I'll pick up next time with the satellite record. The PowerPoint is up on Moodle. I'll go ahead and send out the link once I get this uploaded to YouTube as well. The other videos are still on Moodle, but make sure you're up on exactly what anomalies are, how they're calculated, and then up on the stuff on how temperature records are adjusted, why they're adjusted. You should know what the urbanization and heat island effects due to the temperature record and how those are accounted for. And then know your arguments in terms of, if scientists are fudging the data, what does that mean? We've got lots of different groups, etc. Also, again, remember that 1.1 temperature warming that we've seen since the late 1800s. That's going to be key in a lot of our discussions. Should also remember out of all this that according to our temperature record, etc., that the warming is not uniform. Certain regions are warming faster than other regions. So when we look at things like the ice record, what would you predict if certain regions warm more than other regions? These other records we're going to look at need to comport with and match what your predictions would be if some areas are getting hotter, some areas aren't getting hotter as fast. We need to make sure that all of the different data sets don't contradict what we think that we're measuring, because we need to be really sure about our data. Thank you, everybody. I appreciate your participation. I look forward to seeing you on Wednesday. If you got any questions, shoot me an email. I'm always happy to set up a one-on-one Zoom if you need further explanation or any of that.
Thank you so much, bro.
Thank you.
Okay, thank you.
so
Oh,
much.
one last thing. So up on Moodle, let's see, I have the link to the flip that you guys are supposed to do. Remember, you have a flip recording that you're supposed to do. And I'm gonna go ahead and just bring it out right over here. This is the question. Sorry, didn't mean to do that. This is the question that you'll be answering. Now, since some of you folks don't have access to Moodle right now, I'm going to put in the chat a direct link so you can record your video. So if you're at your computer now, go ahead and click on that link, bookmark that page so you can come back to it. And you don't need to be able to go into Moodle in order to do this assignment, but this is a really important assignment because it gives me a chance to see what you're really picking up from this course. And what I've usually found is if you have to teach something, if you have to explain it, you'll learn it a lot better than if you just paid attention in class. And that's just due in a couple days. So if you can, I will be looking forward. And what you'll get from me is a recording of me watching it and giving you direct responses. So you'll get a lot of good feedback, one-on-one feedback.
Thank you.
Okay, everybody, have a great day. And I will
Thank you, Prof.
Thank you.